Yeah, from Buena State University, and we're gonna talk about co-derivative-based Newton methods. Keep going.
Thank you, Professor Chung. So, please allow me to express gratitude to the organizer. It's my great honor to be here to have presentation in this conference. So today I am in fact I am a student, business student under supervision of
Could
Professor.
you use a microphone? Do you have one
Yeah. Um, So I'm a student of Professor Molokovic, and today I would like to talk about our developed method, Newtonian method, for solving non-smooth and non-convex optimization. So this talk is based on the joint work with my advisor, Professor Phang My Khanh, and my friend Dan Bá Trân. And so the outline of my talk is 5 parts. First of all, I will recall what is the Newton method in classical case, and how do we develop Newton method in non-smooth optimization by using co-derivative, and I need to recall some tool of variational analysis, and after that I will present our convergent analysis of our developed Newton method, and finally we will give some applications in some models. Okay, first I need to recall what is a Newton method, right? That is the C2 smooth case. So we consider the system right here, and one phi here is a C2 smooth function, right? And the Newton method is just like we start at x0, and then we construct the sequence like this, right? And in classical analysis, so this algorithm is locally verified and superlinear converges to a solution X bar if we have the condition like the Hassan matrix and the solution is not singular. And in this case, we have the convergence of this method. Okay, so here the natural question is, how should we develop this method in the case the function phi is not C2? Okay. And the idea here is just replace the gradient by subdifferential, and we replace the Hassan matrix by second order subdifferential, right? Like this. And if we do like this, so we have the sequence will be like this, right? Okay. And then if we construct the sequence like this, some questions arise. First question, when the second order differential system like this have a solution. Why? Because when we construct the Newton method, we need to find the direction, right? So here, if we want to find the generalized Newton direction, we need to solve this inclusion. That is the first question. And the second question is, if we construct the direction, then we have the sequence. So do we guarantee the convergence of this sequence? And if this sequence converges, what is the convergent rate? That is the second question. And the third question is, how do we apply our method to solve some non-smooth radical models? Okay, that is 3 questions. Okay. Before answering these questions, I need to recall some tool of variational analysis. Okay? And you can find more detail in the book of Professor Molokovic and Professor Rockefeller and West in these references. And here I need to recall some definition of normal cone, co-derivative, and subdifferential. And the co-derivative is a general line of the Jacobian. Is when f is the C1 smooth, so the co-derivative of f reduced to the transpose of Jacobian, and when phi here is C1 smooth, so the subdifferential reduced to the radial mapping. Okay. And similarly to the definition of the second derivative of the second derivative is the derivative of derivative. So the second differential is defined similarly like this. So we see co-derivative of the subradial mapping. Okay? And this notion is defined in the paper of Professor Molovic in 1992. And here, if phi is C2 smooth, so the second order subdifferential reduced to the Hassan matrix. Okay, so now we move on to the convergence analysis of our co-derivative based Newton method. Okay, to do this, we need to answer the first questions. When the second order subdifferential system has a solution. Okay, that is the first question we need to investigate before we construct the sequence. Okay. And here, we need to go back to the case when phi C2, this system had a solution if we have the Hassan here is not singular, right? In this case, we can find D by solving this linear system. But in the case phi not C2, we need a corresponding property to guarantee the solvability. Okay, we need to know in the C2 case, we need the non-singularity of Hassan matrix, but in the C2 smooth case, what is the corresponding properties? Here is the definition of some property we need to use. That is the metric regularity properties. Okay? Here is the definition of the metric regularity subregularity. And here you can see it like F it can provide an arrow bound for in the left hand side you can see we cannot calculate the distance between X and the inverse mapping, but we can estimate the distance from X to the inverse mapping by using the distance of the image and the whiteboard here. And this can call the metric subregularity. And if we have the this property, so we call it a strongly metric subregular. And if this property is robust around the neighborhood, so we call it a metric regular. And if we have F negative, we have more properties, so we call it strongly metrically regular. And here we have some results about this. The first result is if we have the graph of subradial mapping is locally closed and the subradial mapping is strongly metrically subregular at this point, then we can find the direction B satisfying this inclusion. That is the first result. Okay, the second result here is if we have stronger properties like strongly metrically regular at this point, then we can we have the robust solvability. That means we not only solve solvability at this point, we have the solvability around the point. And then in some cases, we can guarantee the solvability under the metric regularity condition. If we have the function phi here is continuously regular and satisfy the tri-AB differentiabilities at this point. So to find more about the concept of regularity and tri-AB differentiability, you can find the book of Rockefeller and West, and the fruit of these results can be found in our paper. Okay, that we solved the first questions about the development of Newton method. So the question 2 is, can we guarantee the convergence of the sequence generated by our method? Here's our method, and how we guarantee the convergence. Okay, we answer this question in the C11 smooth case first, and then we develop in the non-smooth case. For C11 smooth case, the method should be like this. Okay, should be like this. And in this case, we need assumption like semi-smooth star. Okay, here is the definition of semi-smooth star. It is the generalization of the semi-smooth property. The semi-smooth property is defined just for locally elliptic mapping, but the semi-smooth star here defined for the set value mapping. And it is defined in the paper of Scheffler and Ochata in 2021. And here example of semi-smooth star mapping. Okay, so under the semi-smooth star property, so we can guarantee the local convergence of our algorithm. We need some assumption. First of all, the considered point must be the critical point, and we need the second order subdifferential system has a solution. That means we need to find we can find the Newton direction, and for the third property and fourth property is we need the metric regularity condition of radiant and the semi-smooth star. If we have these properties, we can guarantee the convergence of the algorithm. Okay, and the root of the method can find in our paper. And if we have more conditions, that means that X bar is still stable, local minimizer, we can get more conclusion. That means not only the convergence of the sequence, we also get the descent direction property of decay of the direction, and we can also get the convergence of the value sequence and the gradient sequence. We get more properties, and this result is also established in the paper of Modovic and Sarabi in 2021. It's overlapped in our paper in the MOR. Okay. The next question is how to guarantee the global convergence of our Newton method. Okay, here is the algorithm to get the global convergence. As you know, the Newton method is only local convergence. So if we want to get the global convergence, we need a Leisner strategy. Here is the Leisner. That means that in this step we relay the TK equal 1 by TK, and TK here is chosen by the arbitrary rule. Amical, sorry. And yeah, that is the algorithm established in our paper in Madurami and Chogo. Here is the result. If we have the second order subdifferential is positive definite in the level set, so we can guarantee the sequence, the convergence of the sequence, global convergence of the sequence. And moreover, we have the convergence rate of the value sequence and gradient sequence, and at least linear convergence, and that is the convergence, global convergence of our result. In the case function phi is C11 smooth, and the second order subdifferential is positive definite. Okay. The natural question is when this algorithm attain the superlinear convergence. When we develop the Newton method, we need the fast convergence, right? We need the fast convergence of this method. But in the frequent result, we only get the linear convergence, right? So if we want to get the superlinear convergence, so we need more condition. That is the gradient mapping is semi-smooth star at the solution point. Okay, that is the additional assumption to get superlinear convergence. So then in next we want to compare our approach with the classical semi-Newton method. And here I will recall the semi-smooth Newton method. That is the semi-smooth Newton method. And the difference between our methods and the semi-smooth Newton method is for the semi-smooth Newton method, the direction is defined by solving this linear equation. And the A here is an element of the Planck gradient. Okay, and here we just find the direction in the by using co-derivative. And our method will be solved by solving this optimization problem. And here is the result. Okay. For GDNM, that is a generalized Dam-Newton method by co-derivative. In the testing problem, we can find the resized formula for D in this case. And for semi-smooth Newton method, we need to solve the linear system of equations. And here we do the numerical experiment, and you can see for here GDNM, that is the time, zero time, and for as a semi-smooth Newton method, that is like this. Okay. And we can see that in our method, so we have efficient than the semi-smooth Newton method, because in this case we can find the resized formula for the direction, while semi-smooth Newton method required to solve the linear system equation. Okay, in the case the second order subdifferential is not positive definite, we can modify the way to find the direction as follows. We can do like this, and in this case we can get the convergence. The first result here is we can get all the accumulation point of the sequence will be the stationary point. And the second result here, we can get the linear convergence if we have the gradient mapping symmetrically regular around the limiting point. And finally, we can get the superlinear convergence if the gradient method is the gradient mapping is semi-smooth star at the accumulation point. For more detail about these results, you can find our paper here. So that all the convergence analysis in the case of C11 smooth. But here we will develop our method to not smooth case. Here we choose a class of non smooth function is this class. That is the sum of two functions, the function f and function g. F here is a convex and smooth, and g here is convex but not necessarily smooth. This kind of problem has appeared in a lot of application. And as you can see in this kind of problem, the function phi here is not smooth. Okay, to proceed to get the convergence, we need to use the forward-backward envelopes for this kind of problem. Here is the definition. And you can see when the function f is 0, then the forward-backward envelope will reduce to the module envelope. It's the generalization of the module envelope, and you can find more about this property in the paper of these authors. And here is the some properties of forward-backward envelope. As we know, for module envelope, we have the differentiability if the function phi is convex or the function phi is Roth regular. So we also get the smoothness of the module envelope. But in the case of the convex function, we have the similar property like this. Here is the properties of forward-backward envelope. If the function f is C2, the function g is convex. So we have the forward backward envelope is C1 smooth, right? And the gradient of the forward backward envelope is calculated by this formula. And you can see we can pass the non-smooth problem to the constraint smooth one here. Instead of minimizing the function phi, we can minimizing the forward backward envelope. And to implement our method to solve non-smooth problem, we need the formula of second order differential of the forward backward envelope. We need the condition to get the T stability of forward backward envelope and metric regularity of its gradient, and the sufficient condition to guarantee the semi-smoothness star of the gradient of forward backward envelope. Because we have the semi-smoothness of the function phi, the subgradient phi, so can we get the semi-smoothness star of the gradient of forward backward envelope? The answer for these questions are positive, and we omit the detail here, and we can find more about the result in our paper. Okay, here's the application. The first application here, we apply our method to solve Lasso problem. Here is the formulation of Lasso problem, and we will compare our method with the highly efficient semi-smooth Newton augmented Lagrange method, and here is the result. And we will use the stopping criteria as suggested by Professor Defensor, and here is the result. And you can see when m is less than n, our method is not efficient than the SNNAL, but in the case m is greater than n, so our method get the fast convergence than SNNAL. And the second application, here we apply our method to solve the constraint optimization problem. Here we choose the quadratic programming, and in this case we will compare our method with just related algorithm, and here is the result. In our algorithm, we get the faster convergence in the case that when the dimension is small and is efficient than the just ribbon method. Okay, so that's all the our development, and in the future we want to establish the generalized Newton method based on the co-derivative for solving non-convex, non-smooth optimization problem. As you know, the co-derivative plays a crucial role in theoretical variational analysis, but in numerical analysis, the method based on the co-derivative has recently been developed very recently, and a lot of non-smooth class of functions have not been investigated. So in the future, we stand to develop our method for solving these kind of problems. For example, in the composite non-convex optimization problem, bilevel problem, something like this. And when we establish the co-derivative-based Newton method, we can apply these methods in solving a lot of problems in machine learning, statistics, and related discipline. Okay, that's all my talk. Thank you for your attention.
Any question so far? Yes, Terry?
Could you go back to your metric regularity thing early on there? I lost track of whether you were assuming this all along, or when you were assuming it, and when you weren't. But you have where you have a strong we have the strong metric regularity of the you're talking about the inverse of the subgradient mapping being, or the subgradient mapping being strongly metric regular at some point, I thought.
Yeah, I
Yeah.
to
Isn't that the same as assuming variational strong convexity? So you're essentially working on a strongly convex problem locally?
Yes, thank you, Professor Rockefeller. When phi is variationally convex, so it satisfies this condition. And the subgradient mapping is strongly regular.
Yeah, so you're basically working on a strongly convex minimization problem.
Yeah, exactly.
Okay,
Locally.
Yeah, locally.
locally, but this is all local anyway, right?
Yeah.
Any other question? I have a question first. So basically, if I understand well, you need semi-smooth star
Yes.
for the gradient,
Yes.
right? And for this condition, it seems like it is true for the case of a union of a polyhedral. The mapping it is a union of many polyhedrals.
Yes.
And I also see that when you go to the application, you stay with the polyhedral functions.
Yeah.
Do you have any application that's out of that condition? Like
That we are working on. That very interesting questions. Our application here is just the regularizer is polyhedral, but I believe that we can move forward to non-polyhedral because semi-smooth star can be certified in non-polyhedral construction.
do you know some like examples that the answer to
Like the norm 2, that is Euclid norm. Yeah,
okay.
Euclid norm.
Okay.
Yeah.
Okay.
So in this case, we can develop like and I can write down here. So for example, we have the function like this, right? Mu x0, x1 that is polyhedral, but x2 is not, right? And some kind we have a norm 0 here. Well, we can.
But it's variationally convex, right? That's
Yeah.
not the issue with L0 model, right?
Yeah.
Okay, variational convex, is it also possible to develop this approach to variational convex?
Yeah, and in some case of model in support vector machine, so I certified the semi-smooth star.
Alright, so maybe let's thank Arthur again.